So, hello everyone, my name is Levente Hajder, and this is the recordings of this Affine transformations stereo vision tutorial, which was originally gave in CVPR 2022. And we had, during the presentation, we had several technical problems, so I record this tutorial again. The video is recorded in the beginning of August. Let me introduce myself first. I'm a researcher at the Eötvös Loránd University Faculty of Informatics, and I am the head of the Geometric Computer Vision group at this university. Here is the table of contents. First we overview the problem and the motivation will be given, and after that we overview the affine transformation, types of affine transformations. Then the standard epipolar geometry will be introduced, and after that several laws will be stated for connecting the stereogeometry and affine correspondences, and several estimators will also be proposed to estimate different geometric properties of the scene or the cameras, the perspective cameras, based on the affine correspondences. This work is motivated by the standard geometry-based computer vision problems. So this set of problems is key in computer science. Nowadays there are many cameras in human life, and usually these cameras can be considered as perspective cameras or can be rectified to be perspective cameras, and then different spatial information can be retrieved from the images of these cameras, including the three-dimensional coordinates, shapes, surfaces of the scene, and the camera parameters themselves are also very important. And even if nowadays deep learning dominates this field, the geometry-based computer vision is also essential for computer science. The standard stereo vision was introduced in the early 80s. And until now, the input for these algorithms are the point correspondences, which means that we have several images, and first the corresponding locations are detected in the images, and then these two-dimensional locations represented by two-dimensional coordinates determine the input for the 3D vision algorithms. And the main goal of this tutorial is how the affine correspondences can be utilized in order to do stereo reconstruction, including the spatial coordinates, surface normals, and the camera parameters themselves. And we exploit both the point correspondences and the affine correspondences, and these affine correspondences extend standard algorithms, and you will see that novel equations can be formed based on these affine correspondences. And if I want to overview the contribution of this tutorial, then I should mention three laws, and these laws are essential for affine correspondences, and these laws connect the affine parameters, the two-dimensional image locations, three-dimensional spatial locations, and the camera parameters. So you will see how these three laws can be written, and which parameters are involved into these laws. A typical 3D reconstruction algorithm, point correspondence based 3D reconstruction algorithms can be divided into several sub-steps. First, it's essential to have calibrated cameras, and usually chessboard patterns are used in order to calibrate the cameras. Then feature detectors and matchers are applied for the images. There are several algorithms. Then the pose is estimated first the fundamental matrix, and then if the camera parameters are known, then the essential matrices can be computed, and then an essential matrix determines the pose of the stereo pair, and finally the three-dimensional information are calculated by triangulation. Okay, this is a standard point correspondence based algorithms. This is the standard, de facto standard in our for the computer vision community, and we will show how these affine transformations can be exploited in these steps. So this pipeline, this stereo reconstruction pipeline, will be modified, and a novel pipeline will be formed. And during this task, several solvers can be constructed, and I hope that I can show you how these new solvers can be constructed. We won't overview all the solvers in very detail, but the basic ideas and the basic equations will be overviewed. The problems to be estimated here are homography estimation, fundamental essential matrix estimation. We will overview that as surface normals can be determined from the affine parameters, and the camera parameters, including the intrinsic and extrinsic. The camera pose can also be addressed. The estimation of these parameters can also be addressed. Now let's overview what an affine transformation is. The affine transformation is a linear transformation, which means that we can write it as the input are two-dimensional coordinates, and the output will be also two-dimensional coordinates after the affine transformation, and the linear transformation is applied, which means that we multiply the coordinates and the affine parameters, and we add these sub-results. So the input will be here the two-dimensional stereo case is considered. So there is a linear warp between the connected image pixels, image regions in two images, and the affine transformations can be categorized as translation, rotation, scales, and skew. And then the main property of an affine transformation is that it preserves the parallelity. So if in the first image the two lines are parallel, after the affine transformation the transformed lines are parallel as well. And the transformation, as it is a linear part, here you see that in the bottom that this equation writes the affine transformations. There are four linear parameters in the left. So P1 is a two-dimensional coordinates. It can be multiplied by a 2 by 2 linear matrix. This is the linear part of the affine transformation, and then an offset is added to the result. So this AU and AV gives the offset vector, which is a two-dimensional vector. And if somebody want to overview the category of the affine transformations one by one, then we can say that the first category is the translation. Here the same offset value are added to both the horizontal and vertical coordinates. So in this case here you see the original. In these examples the original is a square, the original shape is a square, and then it's moved to the top left corner of the resulting image. Then this offset can be written similarly by adding the same AU/AV translation vector to the coordinates in the left image. The second category, the second type of affine transformations is the rotation. If somebody rotates an object around the origin, so it's very important that the center of the rotation is the origin, then it's well known that this 2 by 2 matrix, including the sine and cosine functions, such trigonometric functions of alpha, gives the transformation rotation itself. It's also an isometry. The third type of affine transformations is the scale. There can be two scale link parameters, one for the horizontal SU, the scale parameter along the horizontal direction, and along the vertical direction another parameter SV, should be used. These are real values. They can be negative, of course, if one of the scaling parameters is negative. In that case, there is a mirroring in the transformation. And if the SU, SV, so the horizontal and vertical scale, equals to each other, in that case it's a similarity transformation. Otherwise, it's a general affine transformation. And the last type of the affine transformations is the skew. In that case, the square can, I move back. So for the scales, for the general scale, the square is transformed to a rectangle, and if skew is applied, in that case the square can be transformed to a rhombus. In that case, only the parallelity is preserved, which means that the parallel lines in the left image remains parallel in the right image after the transformation. But it's very important that the angles are modified during a general skew. And the very general affine transformation can be composed of these types. So translation is applied, and so there is a P1 image coordinate. First a skew is applied, then a scaling transformation comes, including different horizontal and vertical directions. Finally, a rotation is applied, and last but not least, the offset should be also used. And here you see that the parameters are a skew, a B parameter for the skew, SU and SV for the scales, and an alpha for the rotation, and A5 and A6 for the translation. And if somebody multiplies these three 2x2 matrices, then the general A1, A2, A3, A2, A11, A12, A21, A22 transformation is given. There is another usual decomposition. Okay, so this is only one decomposition, but several decompositions can be formed for decomposing the linear part of the affine transformation. Okay, this one, if somebody is applied a singular value decomposition for the linear part, in that case, I should highlight that in this tutorial, usually the letter A denotes the linear part of the affine transformation. So if somebody run an SVD decomposition for this linear matrix A, which is size is 2x2, in that case, in the middle there is a scale, okay, with different parameters for the horizontal and vertical scales, and two orthogonal matrices are retrieved, which means that both U and V are rotations in the two-dimensional space. So in that case, the affine transformation can be decomposed into two scaling parameters and two rotating angles denoted by beta and gamma. So in total, in this case also, there are 4 parameters. And it's trivial that if somebody applies this linear, so this affine transformation for a circle, in that case an ellipse is given as the output, as the transformed version of the sphere. And a very important property of the affine transformations, if the translation is omitted, so only the linear part is considered, in that case the affine transformation can transform the lines which go through the origin correctly, which means that all the lines, and if the affine transformation is an approximation of a general transformation, and in that case we select the locations of the general transformation, and the affine transformation is a good approximation to transform the lines which goes over the origin. Okay, so if a line goes, if somebody takes a line which the origin is contained by the line, in that case the affine transformation can transform the direction of this line. Okay, this is a practical property of the affine transformation. Now let's overview the basics for epipolar geometry. So for this epipolar, or also called stereo geometry, as it is a stereo problem, two images are given as the input, and we have a spatial point here, and here is not a point at the surflet, because we will see that if the affine transformations are used, in that case information can be retrieved for the surface as well as the point locations. But in the stereo case, only in the point correspondence case, when only a point correspondence is applied, in that case the spatial locations of this point X can be computed. But in the images, only the projections P1 and P2, the first and second images, are known. These are determined by feature matching. After feature matchings, corresponding point locations are given. They are the P1 and P2 coordinates. All these two vectors are two-dimensional ones, so they are image locations. And the focal point of the cameras are denoted by C1 and C2. And there are two important locations in the images denoted by E1 and E2. They are the epipoles. Okay, they can be given as the intersections of the baseline between C1 and C2. This is a line, and the intersections of this line with the image 1 and image 2, the first and second images, gives the epipoles for epipoles E1 and E2. And the epipolar geometry itself is represented by the fundamental matrix in the general case. General case means that the cameras are not calibrated, so the intrinsic parameters like the focal length are not known. In that case, the fundamental matrix can be determined, can be estimated, and this fundamental matrix defines the corresponding lines L1 and L2. If the cameras are calibrated, in that case the essential matrix can be computed as well. It's well known in the computer vision literature. Essential matrix encodes the translation and rotation between the two images, which they are called the relative O's of the images. And if the fundamental matrix is given and the camera parameters encoded in K1 and K2 matrices, these are upper triangular 3x3 matrices, in that case the essential matrix can be computed from the fundamental matrix. So an estimation is not required. A simple formula can be used to give the essential matrix. Okay, on the other hand, the decomposition of the essential matrix to translation and rotation is a bit more challenging than SVD-based singular value decomposition-based algorithms are frequently applied in order to solve this task. The fundamental matrix, I said a few minutes before that the fundamental matrix determines the two lines, which are called epipolar lines. So if the locations in the first image is given, which is denoted by P1, and the homogeneous representation of this line is taken, which means that from the two-dimensional coordinates we extend these two-dimensional coordinates by a third coordinate, which is set to 1, and we multiply this homogeneous coordinate, this one, by the fundamental matrix from the left. In that case, we get L2 vector, a three-dimensional vector, which represents a line, and this is the epipolar line, which can be given as the connection of the P2, the corresponding point in the second image, and the epipole in the second image denoted by E2. It's a basic statement, a well-known and frequently used statement for the epipolar lines, And the reverse process can also be easily done if point P2, a location P2 is given in the second image, and we multiply this P2, the homogeneous coordinate should be used, of course, and we multiply by the transpose of fundamental matrix from the left. In that case, an L1 three-dimensional vector is given, which represents a line in the first image, and this is the line connecting P1 and E1. This is the epipolar line in the first image. And finally, the last step is to retrieve this here is another basic statement that the epipoles E1 and E2 can be given as the kernel, or also called null vector of the fundamental matrix, or the transpose of the fundamental matrix, and these coordinates E1 and E2 are given by homogeneous coordinates. So the homogeneous division should be carried out after this kernel estimation. And the final task in order to retrieve the spatial location for the point X is the triangulation. So if we consider both point locations P1 and P2, these locations determine two rays in the space, projecting rays, and the intersection of these rays gives the spatial locations. However, due to noise or matching and feature detection inaccuracy, these projecting rays are not connected, and in that case we should find a point, spatial locations, which are close to these two lines. Okay, this task is called the triangulation, and fortunately this task with the fundamental matrix is given. In that case, this triangulation can be optimally used in the least squares sense, and I want to mention that the Hartley-Sturm or Sturm-Hartley algorithm introduced by Peter Sturm and Richard Hartley in the late 90s. So that algorithm, the Hartley-Sturm triangulation, can optimally estimate the spatial location X. Okay, and the last note that if the two locations P1 and P2 are considered, we have one equation which connects this one. This equation connects the point locations and the fundamental matrix. So it's a general equation which is frequently used if the fundamental matrix is applied. And as the fundamental matrix is a 3x3 matrix, but the scale is not, scale hasn't got any meaning, so there is a scale ambiguity. So therefore the fundamental matrix has 8 degrees of freedom. However, this fundamental matrix should be singular, as the essential matrix is singular. Okay, this cross product matrix Tx is a singular matrix. Okay, so therefore the product of this with this matrix is also singular, and this is why the fundamental matrix should be singular, and then therefore the degrees of freedom in the fundamental matrix is only 7. So at least 7 point locations should be given, and if we have 7 point locations, then we have 7 equations like this for the fundamental matrix, and the fundamental matrix can be estimated. However, the most popular algorithm in order to estimate the fundamental matrix is the 8-point algorithm. So the singularity is not considered, only the scale ambiguity. And as I mentioned, the intersection of the projective rays gives the spatial locations for X. In the next part, and this is the main contribution of this tutorial, now I overview the relationship of stereogeometry and affine correspondences. Here at the beginning of this part, and motivating example is visualized, you see that there are two images. So this is a stereo problem, even if only one cameras are given and two images are taken at different timestamps, at different moments. And you see that in the left image there are cars and buildings in the image, and the camera is mounted to a vehicle. And in the second image, approximately 2 or 3 seconds after the first image, another moment is recorded. Okay, and if you see the back side of these cars in these images, you see that the regions of these backsides are highlighted by lines, by white lines, as well as the surfaces of the sides of the buildings are highlighted, many sides. And you see that the magnitude of these regions, of these surface parts, are different in the right image, of course, but the magnitude difference is larger for the back sides of the cars, because in this case I think that this area is 3 or 4 times larger than in the left example, while for the wall of the buildings the difference is not so significant. And this example suggests that the scale of these regions, okay, because the scale difference can be represented by affine transformations, of course. So the differences are significant, or more significant, if an object is closer to the camera, because you see that these buildings are quite far from the camera. And in the right image, the cars which are waiting for a red lamp, so they are closer to the vehicle for which the camera is mounted on. And this example suggests that the scale itself, which is a type of the affine transformations, so the scale itself encodes information for the depth of the object, the distance of the object with respect to the camera. And now let's see the very brief the literature overview of the affine transformation. So here you see several papers which deal with the utilization of affine transformations. The first example is a point correspondence based book, the famous book of Richard Hartley and Andrew Zisserman. And then the affine transformation related papers are listed. Maybe the first paper is introduced by or written by Zoltán Megyesi in 2006, which deals with the estimation of the surface normal from the affine correspondence, affine parameters, but in that case rectified stereo images are used, so this is a special problem. Maybe the first general paper, which also considered with the estimation of surface normals, but also the camera parameter estimation is also considered in this PhD dissertation of Kevin Közer. And then several papers are listed, which was written by the members of our research group. We proposed algorithms in order to estimate optimally the surface normals. Homographies can be estimated from the affine transformations, the fundamental matrix. For this problem, the pioneering work is written by Portuguese researchers Bento Lilla and Francos. They are researchers from the Israel, and they consider the fundamental matrix estimation from 3 affine correspondences. The minimal solution is given by the Portuguese researchers Raposo and Barreto. This was published in CVPR 2016. We also showed that the focal length can also be estimated. In that case, the semi-calibrated case can be estimated. So the camera pose can be retrieved from two affine correspondences. There are special cases for essential matrix, for example, when the planar motion is considered. In that case, only two parameters have to be estimated, and the general camera pose was also estimation was also addressed by the colleagues, and structure from motion algorithm, including the bendel adjustment paradigm, can also be extended by the exploration of affine transformations. Now let's move to the laws. I told in the introduction that there are three rows. I like to call them the first law as the most important law, the second law is the simplest law, and the last law, the third law, will be the most favorite law. I will tell you why I call this, but let's move to the first law, which is the most important law for the affine correspondences. And this law was published first by Dmitry Chetverikov and Joseph Molnar as far as I remember, in 2013, and they consider the general case in the sense that the general camera is given, and for the general camera, so they are not they shouldn't be pinhole cameras, perspective cameras. They are general cameras, which means that there is a projective function. Here it is denoted by P1 and another for the second image P2. And there is a surface, and we take a piece of surface. I like to call it surflet. So a surflet is given. The surflet can be represented as a tangent surface, a piece of the surface. It's represented by a location and the surface normal, but the tangent directions can also be formed. SU and SV are the tangent directions, and N denotes the surface normal. And the projection are given, and the projections are represented by functions, of course, and these functions are denoted by P1 and P2. And if the projected regions are known and the affine transformations are retrieved for affine detectors, then we have four parameters, and these parameters are the input for the algorithms. And Joseph Molnar and Dmitry Chetverikov proved that if the small neighboring region of the locations are given, then they brought first the transformation from the three-dimensional surflet to the image, and local approximation of this transformation can be given by an affine transformation, which transforms from the space to the image, and another transformation can be determined for the second image. And here the gradient of the projective functions should be involved into the equations. The gradient means that there is a projective function Pu for the first coordinate, the u coordinates, and there is another projective function for the v coordinates. And the gradient means that the derivatives of the function with respect to the spatial coordinates x, y, z should be computed. So these gradients are three-dimensional vectors. Okay, and the researchers proved that there is a general relations for the affine transformations which connects the surface normals. It's very important. This is the most important law. Okay, this is the first law which connects the affine parameters, the linear part of the affine transformation, and the gradient of the projective functions are involved into these equations, and the parameters of the surface normals. So there is an equation which connects the four parameters of the linear affine transformations, and the gradients and the surface normals are used for this for determining the affine transformation. And the gradient of the projective functions means that in these functions, both the locations, the image locations, and the camera parameters are contained. Okay, so if we want to compute the gradient of general projective functions, in that case both the image locations and the camera parameters should be taken, and several algebraic manipulations should be done. And in this, the main message of maybe the main message of these equations is that the linear part of the affine transformations can give equations for the surface normals. Okay, so if the standard stereo problem is extended by the affine transformations, so not only the point locations P1 and P2 are considered, but from the neighboring pixels, the affine parameters. Okay, this is the linear part of the affine transformation. If this is estimated, or this is given, in that case, from the affine distortion, the affine warp, the surface normal can also be computed. Okay, so it's stated in the first law how the surface normals and affine transformations plus the camera parameters and image coordinates relates to each other. And here is an example for the gradient. Okay, I mentioned you that in the gradient, here you see the gradient for the first and the second coordinate. The gradient contains the camera parameters. For a pinhole perspective camera, the projection itself is represented by the projection matrix, which is a 3x4 projective matrix, and the elements of this projective matrix, Pij. Here you see that from the first and the second row, the parameters are used, and the u and v coordinates are the image locations. And here you see that the projective depth S is also involved into these equations. Here a small remark that from the last row, from the fourth row column, so from the fourth column of the projective function, for the projective matrix, the first and second element, so P1, 4 and P2, 4 are not used. Okay, so they cannot be estimated based on the affine transformations. Okay, but it's only a small remark, and I think that we won't use it anymore in these equations. Okay, so now let's move back to the equations. Here is the equations, and if the pinhole camera is assumed, the application of the pinhole camera, then we can form several estimators. For example, an estimator in order to estimate the surface normal. Okay, and mathematically, algebraically, the surface normal estimation can be written as an argument minimization problem for the surface normal vector n. Okay, here n is a three-dimensional vector, but the scale is not important, so only the 2 degrees of freedom should be estimated, and we have 4 equations, as there is an equation for all the four linear elements of the linear part of the affine transformation. And in 2015 we proved that this problem can be optimally used, and we proposed an optimal solver. Note that this was published in 2015, as I mentioned a few seconds before, and the optimal solution is given via the roots of a quartic polynomial. However, in 2020 we proved that a cubic polynomial is also exist, and it's surprising that we reconsider the problem by a symbolic tool, and this is a not published result that linear formula also exists in order to estimate optimally the surface normal. The optimally means that optimality is considered in the least square sense. And now let's see the application of the surface normal estimator. So here you see a three-dimensional model show you in 3D. Okay, here is the textured model, and as the surface normals can be computed from the affine transformations between two images, we can add the surface normal to the three-dimensional model. So you see here the normals themselves, and in that case, not only three-dimensional locations and vertices represent the three-dimensional face model, but the vertices becomes oriented vertices, so the perpendicular direction, so the direction which perpendicular to the surface at the selected position can also be given. And here you see the surface normals. However, I should mention that it is a post-processed data. I can show you the original data. Here you see that the surface normals, the computed surface normals, and the surface are estimated one by one, and they are independent of each other, so they are more or less perpendicular to the surface. So here real and non-manipulated, non-post-processed surface normals of my face. And the validation is also very important. So if we are interested in how accurately can be the surface normals be retrieved from the data, we do a test several weeks ago. It's an unpublished results, so we will publish it later. And for the validation, regular surfaces are used. No, they are three planes, perpendicular planes, and all the planes have a pattern, a chessboard pattern, because you know that the chessboard corners can be efficiently and easily detected. And then the spatial locations and the surface normals at the chessboard corners can be computed. Different camera models are applied. Now I only want to show you one example. Here it is seen. Okay, here are the two images. So this is the general case when two images are arbitrarily taken. I go back. Here you see on the bottom left corner the bottom line the two images, and then the three-dimensional locations of the regular chess-based corners are seen here, and the surface normals are also visualized. Okay, and here you see that maybe in the bottom plane, chessboard plane, that the surface normals are not totally parallel to each other. They should be parallel in the noiseless case, but due to the error of the affine transformation detection, the surface normals are more or less parallel. Okay, and in this case, as we know that the surface normals should be perpendicular, the normals of different planes should be perpendicular, so we can quantitatively evaluate the quality of the surface normal estimation. But it was found that the quality is acceptable, as you can see in that image. The second application, and we published a paper approximately 6 years ago, is the camera calibration. As this general law, I show you very quickly, this general formula contains the gradient of the projection function, and the camera parameters are encoded into the gradients. So the cameras can also be calibrated even if the intrinsic parameters are not known. And we showed how this calibration is possible. Okay, for this calibration project, we have here a calibration cube. The geometry is known, the shapes are known. It's regular surface as well. It contains 6 parallel planes, but only 3 are visible at the same time. And we know the geometry of the surfaces, so this can be given as input for the camera calibration, and then the camera parameters can be computed. Triangulation is also possible. Okay, as in the gradient is taken with respect to the spatial coordinates, so the spatial coordinates themselves can be estimated, but this is an open problem in that case, so we don't know. Maybe the PhD dissertation of Kevin Köser contains a special algorithm, but not a general one. So if somebody wants to deal with this problem, then it's a free and open problem, and we believe that triangulation can be more accurately estimated the spatial location if the affine transformations are also considered, not only the point correspondences. Okay, the improvement is questionable, but we believe that the accuracy can be improved, especially for special cases, for example for forward motion or for standard stereo when the pose of the camera is not arbitrary. And another open question, even if we published a paper in an ICCV workshop in 2017, that Bendel adjustment can also be applied, because you know that in the Bendel adjustment algorithm the specialty is that the Bendel adjustment is a numerical optimization in which both the camera parameters and the spatial locations are estimated, and if the affine transformations are used as input data, not only the image locations, the two-dimensional coordinates, but the affine transformations can also be used as input data. In that case, the three-dimensional model of the object is not only the spatial locations, but the surface normals. So the oriented point cloud is the output. And in that case, the specialty of the Bendel adjustment algorithm, the specialty is that the problem is very sparse. So in the normal equations there are many zero coefficients. So this statement remains true, but the concrete form is questionable. So it's also an open problem. In this paper, in the ICCV workshop, we determined the affine transformation from this space surface to the image spaces, so not the affine transformations between the images are considered. So that's a special algorithm, but the general algorithm, we believe that the general problem can also be solved, but in that case the standard Bendel adjustment for the point correspondences can be extended. And in that here in the bottom you see the normal equations, and then in the Bendel adjustment there are many block diagonal matrices, concretely two block diagonal matrices, and the top left, on the top left corner, the shape, okay, the structure of the top left corner is not the same as for the case when only point correspondences are used. So it's also an open problem of the computer vision problem set. Now let's move to the second law. Okay, the second law is the simplest law in the sense that it's quite easy, and this law is related to the homography estimation. So first let's see two examples. It's well known in stereo vision that if a plane is so images are taken of a plane, in that case the pixels of the first image, the pixels of the plane in the first image can be transformed by a homography to the second pixels, to those of the second image, and homography can represent plane transformation between perspective images. And here you see that the border of the chessboards are highlighted by red lines, and the homography can be estimated by standard techniques. It's well known that at least 4 point correspondences are required. At least 4 point correspondences are required in order to compute the homography. If we consider an affine transformation and know that the affine transformation transforms the lines, the border lines as well. However, only two of them are highlighted in the left. One is by red, and then second, the vertical one by green. And you see that if the lines are transformed, the border lines are transformed by an affine transformation, and it is the affine transformation corresponding to the bottom left corner of the chessboard pattern. In that case, you see that the first and the second line, okay, these lines correspond to these ones, so these lines are perfect. However, the opposite lines, okay, which are not visible here, but this is the red line, the transformation of the red line here, the top border and the right border are transformed those, so they are totally wrong. It's clearly seen. And this is why a local affine transformation, and recall the property of the affine transformation that it locally transforms the line directions. So in this location, the lines which contain this point, okay, this is the origin. Recall that the linear part transforms the lines which go through the origin. So the transformations are perfect, and the lines which the lines which don't go through that point, the bottom left corner, are totally wrong. So the affine transformation is a good local approximation, and affine transformation can help to estimate the homography. Okay, this is the message of the second law. So affine transformation can be estimated the homography if we know in which point, in which location the affine transformation represents or approximates the homography. Then these affine transformations can help us in order to estimate the homography. Okay, and now let's consider the standard homography. This is the standard equation for transforming a point by the homography. Here, homography is represented by a 3x3 matrix. Okay, the transformation functions are as here, as they are seen here. The projective depths should be computed. Okay, it's a linear form. Okay, it's given by a fraction, but both the numerator and the denominator are linear. Okay, and the affine parameters here, okay, then this is the novelty here, that the affine transformation is a local approximation of the linear, it's a linear approximation of the projective functions. Thus, they can be estimated by the partial derivatives of the second coordinates with respect to the first one. Okay, and A11 is the partial U2 partial U1. A12 is the U parameter in the second image with respect to the second parameter in the first image, and the AU2 is partial V2, partial U1, and A22 is partial V2, partial V1. Okay, and if somebody computes then the homographies, then this formula can be obtained. And now let's see that, okay, these four equations correspond to the second law. So there are four equations which connect the homography and the affine parameters at a given location. Okay, so here there are four equations, and if only point correspondences are used, it's well known that there are two coordinates, there are two equations for the coordinates in the second image, and each point correspondence gives two equations. However, if we know the linear part of the affine transformations, then we have four additional equations which are seen here. Okay, so we have more equations, and if both point and affine parameters are known, in that case we have 2 plus 4, totally 6 equations from one correspondence. Okay, because you know that local affine correspondences contains both affine linear part and both the point locations. So each correspondence gives 6 equations, and as the degrees of freedom in the homography are 8, only 2 affine correspondences are required, contrary to the point correspondence based case when at least 4 points or point locations, corresponding point locations, are required. So this is the novelty, that only 2 affine correspondences are required for the homography estimation. And there is a special case as well, and we published this result in the journal paper. You see in the bottom of the slide. So there is a special case when the fundamental matrix is known. So the epipolar geometry is known between two images. In that case, only 3-point correspondences are required if only point locations are used to compute the homography, but a single affine correspondence is needed to compute the homography. So if the fundamental matrix are known for a stereo image pair and you know one affine correspondence, then you can compute the homography. And maybe if you are familiar with the decomposition of homography, you know that for the calibrated case, the homography represents a plane, and the plane can be represented by a point and a normal, for example. So only a single affine correspondence is enough in order to determine a plane in the space. Okay, and this is the message of the second law. And of course the plane estimation is possible from one affine correspondence. So in the general case it's not true. In that case 2 affine correspondences are required, but if the epipolar geometry is known, only a single affine correspondence is enough to compute the plane, to estimate the plane. And as a trivial consequence, if one affine correspondence is enough to estimate a homography, we can quite straightforwardly form a multiplane fitting algorithm. We published one possible application in the BMVC 2016, and the plane can be easily segmented as only one correspondence is enough. So each affine correspondence gives a candidate plane, and then we should merge the same planes. And in the top of the slide you see that both parallel and perpendicular planes here, perpendicular here, parallel planes, the plane of stairs here, several book surfaces, book covers can be reconstructed here. Also the walls of a building are reconstructed. So the multiplane algorithm is significantly simpler than for using point correspondences. Now let's move to the third law. This is my most favorite one law, because my own contribution is the highest for this law. We have developed very important equations which connects fundamental matrix and affine transformations. And here you see the mathematical problem. There are two images, and the corresponding point locations are denoted by P1 and P2 in the two images. A small surflet is observed by the images in this case, for which the center is the P1. The center is given by the triangulation of P1 and P2, using P1 and P2. And now we use the following procedure. We move the point from P1 to an infinitely close point in the image, Q1, okay, and the difference between the 2 points P1 and Q1 is epsilon. Okay, epsilon is a small difference which tends to 0. Okay, so here a limit calculation is carried out, and then we compute the epipolar line with respect to Q1. Okay, here is the Q1 which is close to P1, and the epipolar line is here, which is denoted by L2 prime. Okay, and the distance between P2 and this epipolar line L prime 2 is computed. And if we take the limit, which means that epsilon is moved to 0, in that case the value d, which is the distance of L prime 2 epipolar line and P2, gives a ratio, and this ratio shows how the normal direction of the epipolar lines, okay, because I forget to mention that this Q1 is given by perpendicularly move from P1. Here is an epipolar line, and this section which gives for which the distance is epsilon. Okay, this is perpendicular to the epipolar line corresponding to P1. And the ratio of d, the distance in the second image, and epsilon, the distance in the first image, is a very important value because it shows how an affine transformation can magnitude the distance of epsilon along the normal directions. Because if this epsilon is very small, in that case L2 prime is parallel or close to parallel to L2, so the section which for which the length is d, it's also perpendicular to epipolar line L2. And the ratio gives shows the ratio of d and epsilon shows how the perpendicular lines are magnitude, so we can write it for the affine transformations. Okay, so here is a very important equation, which is the equation for the third law of affine correspondences, for which you know that the epipolar lines can be computed as the homogeneous form of the point location P1 should be multiplied by the fundamental matrix. In this case, this is the first epipolar line, the normal directions, so only the first two coordinates of the epipolar line parameters has to be carried out. This is why here a hat f occurs. Hat f means that the third column, third coordinate for the epipolar line is not important, only the first two coordinates. So this is the modified version of the fundamental matrix, only the last row is omitted. And here the tilde f transpose is very similar. In that case the last column of fundamental matrix F is deleted or omitted. Okay, and here is the, after elementary modification, you can find the proof in our BMVC 2016 paper, and after elementary modification an equation can be formed which connects the affine transformation and the fundamental matrix plus the point locations. So this is a basic equation which connects fundamental matrix, point locations, and affine transformations. And this seems to be one equation. However, on both sides there are two-dimensional vectors, so there are two equations, two linear equations, because you see here that affine transformations are multiplied by the elements of f and p1 and p2. Okay, so it's a linear equation with respect to the elements of the affine transformation. The formula can be written in a very similar form. In that case, the fundamental matrix is replaced by the normal vectors of the epipolar lines, and the ratio is given by a real value beta, but this beta can be computed from here. Okay, so this is the another form. So this equation and this one are totally the same, only the parameters are substituted. Okay, so here we have an equation for the normals of the epipolar lines, and the scale is also known, or it also can be computed from the fundamental matrix. So there is a two-dimensional equation system of equations for the affine transformations and the normal directions of the normal vectors of the epipolar lines. So let's go back for a moment. We have an equation which connects affine transformation and fundamental matrix, and so we have two equations, and we can utilize it, for example, in order to compute or to estimate the fundamental matrix if affine transformations are known. You know that from point correspondences there is only one equation per point for the fundamental matrix, but if we know the affine transformations, in that case we have two additional equations, so we have three equations for the fundamental matrix. As the degrees of freedom in fundamental matrix are 7, so if we have three affine correspondences, then we have 9 equations, so the fundamental problem estimation for the fundamental matrix can be computed. Moreover, the problem is overdetermined. Okay, so only 3 affine correspondences are enough, contrary to the case when only point correspondences are used, and in that case at least 7 point correspondence should be known. If the cameras are calibrated, thus the camera pose should be computed via essential matrix. In that case, the degrees of freedom are 5 for this problem, and as we have 3 equations per affine correspondences, so we need only 2 affine correspondences. And in this paper is the paper of Carolina Raposo and Professor Barreto, or our other CVPR paper, you see these equations. It's interesting that the Portuguese researchers get these equations via symbolic toolbox, maybe the MATLAB toolbox, and then the geometric proof is written in our paper. A special case for the pose estimation is the planar motion, which can be used, for example, for vehicle-mounted cameras. In that case, the camera motion is planar. Also, it's a special case when the gravity vector is known. In that case, the camera images can be transformed, can be rectified if the gravity vector is known. In that case, in those cases, the camera motion can be represented by a 2-dimensional vector, 2 parameters, 1 rotation angle which gives the rotation around the vertical axis, and 1 translation direction. So there are only 2 parameters to be estimated, as an affine correspondence can give 3 equations for the essential matrix estimation. For the pose estimation, a single affine correspondence is enough. For the point correspondence based solutions, at least 2 points are required. And as the unknown parameters for the planar motion are, the number of unknown parameters is 2. So the 3 equations give an overdetermined case. We have 1 additional parameter which can be estimated, and we show that if the focal length of the camera is not known, in that case that can also be estimated from a single affine correspondence. Okay. Here you see a video. So the visual odometry problem can be solved. Here we take image pairs from the video sequence at different timestamps, and then the pose between the 2 images can be computed, and we select several image pairs. Then we can concatenate the pose, and we can get the trajectory of the camera, which equals to the trajectory of the vehicle. And here on the right you see the computed trajectory. So the visual odometry problem can be solved. Here you see a right turn, and robustification is also added. Here RANSAC is not required. A simple histogram voting algorithm is applied for the robustification, and you see before this cross that the sun is in front of the camera, which is a challenging case because the contrast of the image is very low due to the sun, and but our algorithm can cope with such difficult and challenging situation. It should be also noted that as only 1 single affine correspondence is required to compute the camera pose. In that case, it's very interesting that local information is enough to compute the pose. For the point correspondence based method, for the standard algorithms, at least 2 points are required. 2 point correspondences are required, and it's better if these 2 point correspondences are far from each other. So in that case, the whole image can be processed, and a global algorithm can be computed, and it is shown here that as only a single affine correspondence is enough to compute the camera pose. From local information, the camera pose can be computed. Another application of this third law, which connects the fundamental matrix and the affine transformation, is the correction of affine transformations. First, let's overview the same method for the point locations. It's the Hartley-Sturm triangulation, which was published in 1995. Here you see that we have 2 points in the images, denoted by a black, drawn by black dots. The epipolar line corresponding to this left black epipolar line is the black in the right. However, unfortunately, the epipolar line for the right point is the red line, and here is the corresponding pair in the first image, and unfortunately the two lines in the images are not the same, but they should be the same. So the correction of the idea behind the correction is to find corresponding epipolar lines, the closest corresponding epipolar lines, and the point locations are projected to that lines, and then the projected coordinates are the corrected coordinates, and then the triangulation algorithm can retrieve the spatial point as well, and in that case the spatial projective rays intersect each other in the space. Okay, this is the Hartley-Sturm triangulation. A technical detail is that the solution is given by a fifth order polynomial, but the same algorithm can be applied to correct the affine transformations. So if we have an input affine transformation between two images, then this affine transformation should fulfill the equation, the third law for which connects fundamental matrix or normal of epipolar lines. And in that case we have two constraints for the affine transformations, so only 2 degrees of freedom remain for the affine transformation, and the problem here can be solved by applying 2 Lagrangian multipliers, and the solution is given by a 6-dimensional linear system of equations. So the problem is linear. You know that the 4 affine parameters and the 2 Lagrangian multipliers should be computed, but the problem is linear, so it can be quite easily computed. And this correction algorithm is extended by the colleagues in 2019 for the multi-view correction. So when there are multiple images and multiple affine transformations can be retrieved from the images and they can be corrected. And finally, I would like to conclude this affine correspondence utilized theorem. So we can form a new 3D reconstruction pipeline, a structure from motion pipeline, which utilizes the affine transformation. And here see that the input images are the input for the pipeline, of course, and the output is not only point clouds but oriented point clouds. So each point has the surface normal. So each point has a normal direction. And the pipeline, the first task is to compute the fundamental matrix from using point correspondences. Then the affine transformation can be retrieved, and the correction algorithm, this one, can also be used. So the affine estimation will be more accurate, and then the fundamental matrix should be recomputed using both point and affine correspondences. And then if the cameras are calibrated, then the essential matrix can be computed. It can be decomposed into the camera pose. The triangulation problem can be solved. And if we know the spatial spatial coordinates and the pose, then the surface normal can be used utilizing the affine transformations, of course. So the affine transformations can also be stacked into this algorithm, and then the surface normals are computed. Okay, so here the oriented point cloud of the scene is computed, and if we have more stereo image pairs and we run the same pipeline, this one again and again, and at the end a Mendel adjustment algorithm can also be implemented, and this refines all the parameters, including the camera parameters, the three-dimensional coordinates, and the surface normals. Okay, so the novelty here is that the surface normal can also be computed. And finally, I would like to show you an example. Here you see that the three-dimensional model. Okay, this is the output of a standard three-dimensional model, but the affine using the affine parameters, the surface normals can also be computed. So you see that these normals are more or less perpendicular to the wall of the building. I hope that it will be visible in the video as well. And finally, I would like to deal with the estimation of affine correspondences, because in the affine correspondences, because in the previous parts in my talk, several laws, three different laws have been overviewed, but the input for all these laws are affine correspondences. But I haven't told anything about the retrievation of the affine transformations, because it's not a trivial way, and unfortunately it's not a deeply researched research area. For the point correspondence matching, there are several algorithms. First, the feature corners are retrieved, and descriptors are computed for the corners. This is the usual way, most frequent way, and finally, based on the descriptors, feature matching are applied. And here you see several types of features. I don't want to go into the details because I am not totally familiar with these topics, but I would like to show you another way, because line matching can also be applied in order to determine the affine correspondences. Usually point matchers, so by the hacking of these feature matching algorithms, the route estimation for the affine transformations can also be retrieved, but so I can't offer you the best way, because I think that's also an open question in this field, how affine transformations can be retrieved very accurately from the images. But I want to show you that the line correspondences can also be applied in order to retrieve the affine transformations. Here you see that we prefer the application of S-SIFT algorithm, which is a affine SIFT, or we have modified, my colleagues have modified the other algorithms, adding the same trick as in affine SIFT algorithm. For the affine SIFT algorithm, the images are transformed by several affine transformations, and then the SIFT algorithm is run again and again, and using the affinely transformed images, more feature points can be feature matching can be retrieved from the image pair. However, the affine transformations can also be retrieved, as the applied affine transformation is a good approximation for the real one. Now let's see the application of line features. Okay, the one I tried to highlight that a very important property of the affine transformations, concretely the linear part of the affine transformation, is that it transforms the line directions correctly, which goes through the origin. So we can write an equation for these lines. If we have L1 line line L1 in the first image and we multiply it by the affine transformation, then the second direction L2 can be retrieved. However, the scale itself is not known, or it can be known or unknown. If it's known, then alpha is known. Okay, this is a real value, a scaling parameter. Otherwise, alpha is an unknown parameter which should be involved into the estimation of the affine parameters. Okay, so there are scaled and unscaled directions, and a very important thing that we can apply the third row which connects affine transformation and fundamental matrix, because it gives two equations as well, and the scale itself, you know, maybe you remember that the third row connects the normal of the epipolar lines, and the scale itself can also be estimated if the fundamental matrix, the epipolar geometry between the two images is known. So we have a scaled line pair for the two images. Yeah, so if we have multiple line correspondences between the two images which goes through the same location, in that case the origin should be moved to that location. Okay, this translation gives the translation part of the affine transformation, and then if we have two intersecting lines, then they can give more equations, or we can have multiple intersection lines, of course. And there are different ways. We published very preliminary results 2 years ago in 2020 in our paper. So we can estimate the affine transformations if two unscaled and one scaled directions are known, or we have one scaled direction and the fundamental matrix, or we have two unscaled directions and the fundamental matrix, and so on. So novel algorithms can also be applied. Okay, this is the theory. This is a very theoretical paper, and for the practical applications, I think that there are space to improve the algorithms. There are possibility to improve the algorithms. Okay, so finally, I would like to conclude my tutorial talk. The topic was the affine utilization of affine transformations for stereo vision problem. I think that this is a new and very important research field within stereo vision. Here, three geometric laws have been stated. One, the most important one, which connects surface normals, affine transformations, and camera parameters, projective functions. The second one, which was quite simple, because the equations were given by simple taking the partial derivatives of the homography, but four equations can be formed which connects homography and affine transformation. And finally, the third law was equation, a two-dimensional equation which connects affine transformations and the epipolar geometry. And here we have overviewed several novel estimators for estimating the surface normals, camera parameters, fundamental essential matrices, pose for planar motion, and several application areas and examples have been overviewed. We visualized how the surface normals can be obtained, for structure from motion, Bendel adjustment, result of a Bendel adjustment, an over Bendel adjustment algorithm has been overviewed. We have shown a video for the odometry problem. We have examples to multiple plane fitting algorithm, and I think that I have listed all the shown examples, but there are open problems in the field, and I highlight here only three problems: the triangulation, the optimal camera calibration, the general Bendel adjustment algorithm, but I think that there are many other interesting problems for which the affine transformations, the affine correspondences can be utilized. So thank you for your attention. I hope that I can give you the importance of the utilization of affine transformations.